Okay, good morning, dear participants. I welcome you all to this day 5 of the AICTE ATAL Faculty Development Program on Finite Element Method and Product Design. It's my pleasure to introduce to you today Shri Vivek Chavan, Scientific Officer H of Refueling Technology Division of BARC Mumbai. I have had fruitful technical interaction with him over a long period of time. Shri Chavan had joined BRC in 1995 after graduating from BRC Training School. He has completed ME in Mechanical Engineering from Indian Institute of Science, Bangalore. Shri Chavan has made outstanding contributions in the area of dynamic structural analysis and experimentation, which has helped in development of special facilities and equipment subjected to severe dynamic loading conditions. His expertise in explicit finite element analysis coupled with meticulous work has helped in timely completion of several safety projects of importance involving impact analysis and evaluation of numerous shipping cask designs used for transportation of radioactive material. As a group leader, presently he is leading a team of 4 engineers working in structural impact analysis and testing group in refueling technology division. He has supervised several MTech projects enrolled in Homi Bhabha National Institute. He has also delivered training courses on applications of explicit finite element methods at Indian Nuclear Society. The chairman of Atomic Energy Commission has conferred Special Contributions Award in 2013 and Young Technologist Award in 2006 on Sri Vivek M. Chavan in recognition of his outstanding contribution to the department. With his brief introduction, I now hand over the session to Mr. Vivek Chavan for beginning with his first session of the day. Vivek Chavan, please. Yeah, I have a question. If at all you have to introduce damping in the problem, can you just give us some, information as to how do you introduce realistic damping into the problem?
Yeah, good question. See, first of all, damping is very important when we do some kind of small deformation problems or frequency analysis kind of problems where displacements are very small. Okay, that time, I mean, damping is important everywhere, but the damping matrix which I ignored during my the basic analysis. So there you introduce through the C value or the damping. There is a parameter which you can introduce, and that gets associated with the velocity. And all throughout my application of equilibrium equation, I just use the K term and the mass term, but additional term will get associated. That is number one. But when I am actually solving the explicit time integration or applying these methods, explicit FE methods to solve highly nonlinear systems, there I did not worry about this C matrix a lot because the damping of the system is really due to the material behavior, material flow. Okay, so material goes into plastic deformation and so on and so forth. So there I did not worry about this kind of Coulombic damping or the C damping. So there were two things. I can still account for the friction if there are any between the adjoining bodies and surfaces, and there will be definitely the friction. So that frictional energy I can account in my calculation, and the real damping comes from the material flow or the plastic deformation.
Okay, so fine, but my
So,
question in more general sense, if you take, if
to
I
in a
have,
just in short, to just shortly to answer again in the one line, the damping is introduced in explicit solution by the way of material models itself.
okay, okay. Vivek, there is one more question on the in the chat box. I'll read it for you. Okay.
Yeah, yeah.
In explicit method errors accumulate and the answer may diverge from the expected one. But explicit method has reduced errors as the simulation progresses. So why we use the explicit methods? Please give guidance.
Yes, very good question. See, as I said, there is something called divergence of solution or the stable solution. Okay, there are only two things. So there is only one criteria on the time increment, that my time increment between some number, and that I said that is the current criteria which is associated with the shortest length of your mesh. Now this length is actually quote unquote length term, because in 1D element length is directly element of the length, but in 2D and 3D you have to compute the effective length. Okay, having said that, once your stability criteria is met, you can rest assured that solution will not diverge. Otherwise, it will diverge. Solution delta t if it is higher than that. But then, as I said, even if it is just at par with stable condition or less than that, then it will have errors. And at each delta t, as you rightly said, there will be accumulation of the error. But you have to make sure that error accumulation is within control. And other way of generating errors, or why errors are introduced, as I said, is reduced integration. If you do full integration, then perhaps that part will not come, that hourglass problem will not come. But invariably all the codes use the elements for FE, explicit FE, which are based on the reduced integration to reduce the entire time of the solution. And so that is one part you will have to control, and there are many algorithmic schemes available to address this. So they use algorithmic damping, something called as algorithmic damping, to control the hourglass error and all that. So I hope
Okay.
that answers. Yeah.
Okay, there are, you said about the softwares that can be used for this analysis, but one of the
Yes,
participants wants to know which is the best software.
yeah, no, and no, let me complete that first question also. That
Sorry. Uh,
uh, why explicit methods are used? Again, normally for linear systems and all, there is no need for that. You can do very well with implicit, and you will have convergence criteria, and then you are happy with your solution. But in case of large deformations and large non-linearities. If you use implicit solution, life will be miserable because you will never get the convergence. No matter what, you will never get the convergence. Okay, so then what to do? So either you accept little bit inaccurate solution for a very complex system, or then if your system is simple, then you go for accurate solution. So it is like this. So that it works like this. Okay.
Okay, you have to see for the trade-off. Okay.
Yes. So this is a trade-off. So if you are
Yeah.
doing simple systems, okay, you go for accurate solution. But if you are dealing with very complex problems and solutions, then you accept solution with accurate with little bit inaccuracy, and that's what the verification comes into picture. You have to be very careful about the solution, the quality of the solution. Yeah,
Okay.
and which
There
is the
are,
best? Which is the best software? So
yeah.
there is, yeah, obviously we want something like a best cow which eats less and gives more milk like that. So there is nothing like best. Okay, so there is a compromise only. So there are few more practical things. Something like one is availability. Like for example, we are a sensitive organization in the country, so therefore we are under sanctions from all the developed countries. Most of this software originate from developed countries, and particularly one, that is America. So they will never give us for our use. So that is one part of it. If anything is good but it is not available, what is the use of it, isn't it? So, but anyway, but
Yeah.
people large at within country, all industries and academics, there these softwares, all kind of softwares are available. Now, one will other criteria is the cost of it. These are, of course, these are technologies. These are not just softwares. These are very highly developed technologies and tested and verified. So the cost involved is very high. Okay, so you have to compare on the cost front also. Other is, of course, the algorithms they give and the kind of problems they have solved, so and so forth. Just graphics point of view, GUI, the input and the output, that remains more or less same for all. But the important thing you need to consider is the solver. And then there are different solvers, as I said, LS-DYNA, Abacus Explicit, Crash, Radios. So what you need to really see is what kind of problems you are going to solve. Suppose somebody is in automobile crash, in aerospace modeling, in defense field, explosives and all that. Then you need to see what are the algorithms they have given in the code or in the solver, and how accurate they are through various problems you will have to solve. So based on that, you will have to evaluate. Otherwise, the for a user, let's say for a beginner, everything will appear same more or less, whether it is Abacus Explicit or actually the beginning of all these explicit codes started at Lawrence Livermore Lab, which is again a nuclear lab in USA way back in 70s. Somebody called John Holquist, he started the development of this family of finite element codes. And more or less all the codes, barring maybe Abacus Explicit, is a extension of this original Lawrence Livermore code only, Holquist code. Okay, whether it is Crash or Radios, or of course the LS-DYNA. Then there are other codes also with the time, not now they are no more in practice. But the Abacus came up of the late only. They were very strong and implicit, nonlinear also. But of the late they have also developed Abacus Explicit. So I will say yes, that is one of the very good sought after code.
Okay. The best book.
The best
Book.
book. Okay.
Yes.
Who reads book nowadays? I don't remember having gone to library for long. Yeah. Yeah, of course, internet PDF or PDF kind of books are available. But I will say, okay, as such for explicit methods, you will find from numerical any book on based on numerical methods. But the algorithms, what is important is the material algorithms and nonlinearities, which you have to understand. For that, I will suggest MA Crisfield. MA Crisfield, the 2 volumes is there. So that is basically will introduce to the physics of the problems, and these are implemented numerically in the codes. Okay, and numerical methods are separate part of it, and the algorithms or the material models is a separate part. So important is to understand these material models, because they are basically simulating the response of the physics, or they are giving the numerical value to the response of the physics. So you have to combine different books, and actual implementation, how it is done, that you will find from the manuals of these codes. Okay, so these codes, they give very good elaborate manuals, and they elaborately explain how it has been implemented. So even if you study manuals of any one code, say LS Dyna or PAM Crash, then you can pick up a lot of understanding behind its implementation.
Okay, that's a very practical suggestion. Good. There is one more question. The participants wants to know that for performing machining simulation, which method may be more suitable, explicit or implicit?
Yeah, machining basically is removing of materials, right? Either it
Yeah.
could be either a turning or kind of a drilling. You're talking about that, isn't
Yes,
it?
yes. Machining is that. Yes.
Or a kind of milling. Yeah. So in that case, definitely I will say, because there is a removal of material from that, so it involves few things. Something like even the friction is there. Then there is a fracture criteria is involved. I mean, the chips, how the chipping occurs due to some fracture, and then there is a heating of the job also takes place due to frictional heating. And so if you see, if you are applying any differential equation, you can see so many non-linearities are involved. The material itself is getting lost. The boundary conditions are changing. There is a heating of the material and fracture of the material, fragmentation. So definitely you have no option but to use explicit method, explicit FE, to carry the simulation forces.
Okay.
In implicit, it is highly impossible to get any convergence.
Okay. There is one more specific question. He asks, he's perhaps doing something, it seems to me. One, Mr. Sam Joshi is there. He is asking, sir, at what time we came across at one time we came across Jacobian error in explicit modeling of metal forming. Any ways to avoid such errors?
Yeah. So Jacobian is a very common error. Actually, that is the error. That is because your stability criteria was not met. Okay, one number is, second number is the Jacobian goes negative if the problem is not correctly specified, or in a way, what I will say, as such. Okay, as such, these explicit methods are very tolerant. Like suppose a problem is ill specified in terms of boundary conditions and in terms of loading, then implicit solution will not come, because matrix inversion cannot occur. That matrix determinant, if it is zero, then solution won't come in implicit. But explicit methods are not that stringent as such. But definitely, if there is a kind of a flipping of an element occurring somewhere, flipping means what happens is, how do I explain? It is easy to explain on the board. Flipping means basically a kind of unimaginable physical deformation of an element. Okay, which physically, suppose you have a piece of paper, and you can imagine it deforms something inside out or something like that. So that you can show through figure on a screen, or through a matrix numbers, which is not physical. So if that kind of thing is happening, so that is akin to the Jacobian error in your solution. So to control that, either you have to check the quality of your mesh. Number one, the aspect ratio of your mesh has to be reasonable. So what happens is, if you have very poor aspect ratio, then also these kind of errors come.
Okay, Vivek, that's fantastic. Many people have already written in the chat box that it was very useful and informative session, and many of them have enjoyed it. So many, signs also are coming saying that it is wonderful.